these last time, and one of my doubts that I didn't put in Twitter got solved by I got an answer. Basically, people were like, because I was wondering like how come the current density is something that's calculated with a wave function and not the probability density function. And the answer kind of makes sense, which is that it's because you want to consider the interference effects. I guess I'm not so sure if that's like it intuitively makes sense, but I'm not so sure how happy I am with that answer. But here we are yet there again to try to understand that. And why there's a, and I think a lot of this is just because of my lack of mathematical intuition with regards to these, right? So it's more about the fact that, like, I don't know what the derivative of a wave function times a wave function really actually mean, and why there's a minus and why there's, is all packed into the sinus. This is just like, I look at this like, like you can still try to, it's like, this was rather easy in comparison, right? So is there's the product and whatnot, and that's the way you can calculate the inner product between two wave functions, etc. It's just a mathematical identity. But which still makes sense, right? Because it's trigonometry, right? So the cosinus of the cosine of the angle and whatnot and stuff like this. But these is like, and it's also done with the radius as function. But I've also learned that that's a common observable within just the what I would say the x observable, sort of the physical dimension, right? So you can either just do this in terms of coordinates like x, y, z if you're talking about 3D space, or an r coordinate if this is a radial wave function, whatever, something that just depends on the distance to a certain origin or something like that. It's just a technicality, but why? So I'm and maybe I'll just have to forget about these and try to understand what does the product of something and its derivative, what is sort of the mathematical intuition for these. Like I know the mathematical intuition of a derivative is the gradient, or sort of the I forgot what's the right English term for that, but basically, yeah, like how at what's the function that describes the gradient of the function, right? Why is that even just packed as part of a number? Let's see, Wikipedia. And we're looking for the current density. Current density. Probability current density. Current density. You've got an angle, free currents. We've got integrals, right? That's even more confusing. Where displacement current. In practice, quantum Hall effect. the current density is the amount of charge per unit time that flows through a unit area. I mean, it doesn't matter if it's not related to quantum computing or quantum mechanics, but I think this might actually lead to something. So you use this kind of J thing, so whatever. The current density vector is a vector whose magnitudes is the electric current per cross-sectional area at a given point in space. Assume that A is a small surface centered at a given point M and orthogonal to the motion of the charges at M. If IA is the electric current flowing through A, the electric current density J at M is given at the limit. Yeah, so it's basically, it's just saying how much of this electric current is going through the surface, right? And then you just take the limit on when A approaches 0, so for a very small chunk of the surface. So this is just, the current density vector J is the vector whose magnitude is the electric current density and whose direction is the same as the motion of the positive charges at a given time t. If V is the velocity of the charges at M. This charge is equal to derivative of A. Oh, dA, okay. But it's dA because maybe this has got to do with the fact that we're talking about a small increment or something, right? Current density, quantum Hall effect. Density of states. Current density, no. Probability current. Probability current. Because here, oh, wait a second. Maybe this is something. Maybe I'm approaching this from the wrong perspective. Maybe this is something that is derived out of the continuity equation. So you're saying this can be seen through the continuity equation in the following alternative. Oh, no, but it's an alternative way. Okay, so no, it doesn't matter. You've got a surface of omega-1, and then the interval of that surface, the sort of the small increment, a small portion of that surface times that. And then why is that replaced by the derivative of these over time? What the heck? That's going to be another hell of a what the heck. How do we even parse that? Current density is easily computed to be these. Probability flux. Probability current. I just want to find that function, right? Oh, I mean, okay. We got it. This is it. I think that's the starting point. Is it? No. Fuck. H bar divided by 2 times m. It's almost these, right? Because where the fuck is that sinus? Oh, unless unless we're saying starting with the same initial wave function, so that's the wave function. So that's the wave function, okay? Yeah, maybe this is just the result of how this has been elaborated. You know what I mean? Let us see. So we start with this wave function. This is the wave function we have. But that's just the initial wave function, right? So I need to add like a term to it. This is still from the last time. And so the initial wave function is so psi of x of 0 equals of psi 1 of x, psi 2 of x, these being the eigenfunctions. Yeah, that's the what happened? There you go. What have I pressed? And now basically what we're saying is probability density, yeah, real and isotropic. Take the two partially overlapping regions to be two concentric spheres. Compute the probability current that flows through omega 1. Maybe I guess that is what allows us to do things in terms of R, maybe, right? Because they are isotropic, so it doesn't matter where you are. That's yeah. So that is actually what I just deleted before. This thing with that is what being isotropic and being everything concentric means. It's like everything can be expressed just as a in relation to the radius, to the center of these two concentric areas. I think that is why, although it's not explained in the solution, that is why you can do that, right? So I guess instead of X, you can just say R, right? Whatever that means, I don't know. That just like, I don't know why would that make a difference, but and then the probability current that flows through omega 1, right? Flows through omega 1. But then in non-realistic quantum mechanics, the probability current of a wave function of a particle of mass m in one dimension, yeah, maybe it's because if we're using R, then we can treat this as just a one dimension, so we can apply that specific probability function, because otherwise we would have to pick another one. So maybe that is why you need this to be isotropic, and you need to be it just makes it easier, right? So we know we can use this. This is a good starting point. Cool, but like what bothers me. I mean, we have the wave function. Okay, so we have the wave function. Yeah. So we have the wave function, which is just these, right? And so we take that, that's the wave function. So we do that. I guess that's how R goes out. I'm sorry, I should maybe think a bit better out loud, right? But it's like you're, so what we're saying probably is that we can say that we can define that in terms of R, so it's just one dimension, right? So we can just literally say, and I don't know if you can just get rid of the time though. R. And sorry, what am I doing? This is just 1/2. This is just 1/2. So this is the, let's say this is the wave function. And then so we have these. Can I just do that? Probably I can just. Yeah, there you go. So. So, you know, so we would go ahead and say, well, so this whatever thing here, right, is these h bar 2mi and then times, right? And so now we would say, cool, so the wave function complex conjugate is just the same because we know it's so we know it's it's real, right? So let me try to do that aside. So we just have 1/2 and then we have these plus psi 2r, and then we have the derivative of these. So we have these times with respect to x, with respect to that one dimension here, this is x, but it should be r, right? So that takes the r out. What? No, sorry, what am I doing? What am I doing? No. So basically, the derivative of these is just the derivative of that, right? I mean, like essentially, because I don't know what those things are, then that's the same like just saying the derivative of these functions, right? So I mean, and then we have, so then you basically have you know, let's just do that, and then we have these things, you know, like psi 1 times psi 1 derivative plus psi 1 times 2 derivative. Okay, and then we have the psi 2r times psi 1 derivative, and that's tedious, but let's see. And the thing is, we're gonna have these and minus, you know, kind of the same thing, right? So I have no idea, because that that should be 0, right? That should be 0. I mean, but no matter how you look at it, that should just be 0. Because Kinetic momentum operator. I don't get it. I don't get why are we doing it this way if they are real. To me, it just seems obvious that that should be 0. Not saying it's not, right? I mean, although here, that's the thing, right? So here we have this, which I just have no idea what the hell is this coming from. Fuck easily computed, man. That's definitely not easily computed. I mean, it's easy if you know that, but how to get there? Because here you get all these derivative terms and whatnot. Maybe some of these things just cancel out. I don't know. But still, where do you even get that thing here from? And why does this vanish at R1 since one of the other eigenfunctions vanishes at that point? Oh man, I don't want to it's free spin 0 particle. You know, electromagnetic field, connection with classical mechanics. Why is that? Let's assume that the first component is somewhere associated with the mass, right? It's just because in the classical sense, you have that the mass flux is the mass density of the fluid and then the velocity. So maybe the reason you're doing those derivatives and stuff is because of that's what you want to do essentially, right? You want to calculate at what speed things are changing. That's why you do the derivative. But I don't know why you do the derivative times the wave function, right? The mass density, whatever, I'm going to just assume that that's what this term is equivalent to, this term in here, and then probability current. First, consider the usual arbitrary approach based on properties of a given arbitrary wave function. So the wave function evolves according to the Schrödinger equation and its complex conjugate satisfies. Well, the squared wave function gives the probability density, so the charge density is defined. One can get the current by looking at the changes of the charge density with time, which depends on the changes in the wave function squared. Ah. So you're getting these terms from the fact that you're observing. Okay. That makes a bit more sense. I didn't know that. The derivative, of course, the derivative of these, and this is just probably whatever chain rule or something like that. Derivative of the derivative of product of functions or something like that. That's just whatever the rule is, right? Yeah, I guess. Yeah, there you go. That is why. You see, it's always satisfying when you find these things. That actually explains why. Not the sine, not why the sinus function is there, but it explains why the fuck is this? Because yes, because it's the derivative, it's the derivative of the probability density. And so I'm pissed now because I'm pissed because Twitter just gave me the wrong answer. I think it's like I was like, why is that defined on the wave function and not the probability density? Well, it is defined on the probability density. It's just but why a minus? Why a minus, not a plus? Why a minus? Maybe I don't make too fast with this stuff, man. Because it should be a plus. No. Why? Fuck. It should be a. Maybe this is just why the minus. Oh, look at this. What is this? Okay, so this is what we're looking, almost what we're looking for. The Hamiltonian has the non-relativistic form where the potential is assumed to be real. The EM potentials A and technically must be real, whatever that means, because they describe the real electromagnetic field. At some points, the calculation may be taken as complex, but always it is assumed that such expressions have an implied extra complex conjugate term to make the total real. Using this Hamiltonian, the potentials cancel out and only the kinetic energy terms remain. Okay, so wait a second, why? And now here's a minus suddenly, right? Whatever the fuck pi here is with this vector thing on the top. Dude, I've never seen this. Well, unless what these guys are doing, essentially is taking these basically and doing the derivative of these, right? So it's these times the derivative of this whole thing, because that would explain the sinus. It's the only thing that I can come up with, you know, that explains these. Because the derivative of cosinus is just, it's minus sine of x. Man, but that's the only thing I can come up with. No, but that also wouldn't make sense. I don't know. I just don't know. I don't know where. Where is that coming from? I don't know. That is the rate of change. Fuck, man. Of the probability density function. Where is that coming from? God. The current density can be computed to be these. Like, how do I even get there? But let's recap for a second. I'm happy that at least I opened up these, because these is look at this guy, right? So let's think about this for a second. The E. But that E, that's something else. I think that is... From the continued equation, one can get the current by looking at the changes of the, yeah, like that. That is just intuitively, I understand that is, you want to take a look at how the probability function, how the probability density changes, right? So you want to do the derivative of that. Okay. So you want to do the derivative of that, right? So this is like, if I would just start from that perspective, where would that take me? Derivative of these times itself plus derivative times itself, right? Where is that taking me? So this is just what I would think of, and let's just maybe take that, right? If there is overlap, the probability density will be, let's just take these as a starting point. So we have like a we have the half x, whatever x, if this is like r, whatever, it doesn't matter, right? Squared plus psi 2x squared, and then we have, so this is one term, and then let's think about this term, right? The other term, let's think about this term first. So what, because it seems to be like, in a way, it's vanishing or something, but I don't know. So what is the derivative of an absolute square function? Oh, well, a derivative of a function squared, I mean, I could just follow what I just learned, right? So but I mean, okay, let's just say to give okay, define, okay, cool, that's a new way to do it, yeah, of course. So I can just say the so you know, so the derivative of this one, right, is the derivative of the sum of functions. Is it just the sum of derivatives? Yeah. Okay. Thumb rule. An absolute value of a function. Is there anything there that I should? Is there anything specific to be aware of? Because that's a bit messed up, right? But okay, the derivative of these would be basically, you know, kind of like, so we have, you know, we have these, and so derivative of these would be like, the twos will go. So the if I would do the derivative of x, you know, of that with respect of x, sorry, of that thing, so it would just basically be the derivative of x, right? And then here we just get like the derivative. So yeah, so that's what you'd get, right? Assuming, yeah, like I don't know, I really don't know how the absolute values will play a role here, but let's try to approach this block by block. Cool. And then the derivative of these is fucking complicated. Because what does that cosine in there mean? I don't know, man. But it seems to me that this is gotta be I don't know. I don't know. Because I don't know, I don't understand how is that defined. We have set psi 1 2 equals the absolute value of times this. Don't remember. How the heck did I even get there? If I take a step back and I take a look at how, so it's basically, right? So let's take these. Let's step back a second. So let's take these here. So we have this definition, right? So we have that psi of xt equals e to the power minus I energy times whatever h bar. So that's just like the generic way of saying whatever evolution of psi 1x, right? No. Sorry. Of that. So I think that was the premise here is like in the initial state is these, right? So you want to get like first of all this expression. So that is, you know, times psi x0, right? Just to abbreviate. We know it's this thing here. And so if we want to do the absolute value square, if we just want to do the probability density, the probability density is you know, it's basically this times its conjugate. Okay. Two eigenfunctions are real and isotropic. Well, anyway. So we do these times the conjugate. So the way we do this is basically saying cool. So e minus I e t divided by h bar times psi x0 times, and then the conjugate here would be e to the power of like plus I. We're conjugating these, right? So h bar times the conjugate of these is just the same because they are isotropic and real and whatever, right? Now these two things here add up to just say, well, this plus this is just 1. So I think these two coefficients disappear, right? Because they become 1. And so we end up with just basically having to square the initial function. So we just basically have to say that the probability density function, the probability density is basically the square of these things. So we have that's why we have 1 divided by 2, and then we have that whole thing here, psi 1 of x plus psi 2 of x squared. Let's just leave it here. Am I missing something here? Yeah, okay, no. So I mean, I can expand that, and that's how you get, you know, to this guy here, right? But let's maybe stay here for a second. So let's stay here for a second, and now I just say, look, so that's it, right? That's our probability density function, and so maybe it's easier to calculate from here. If I just take that standard definition where it's just like, well, we get the current by looking at the changes of the density function, right? Like maybe whenever this term is, we're adding that, right? I'm trying to intuitively, you know, reverse engineering that. I'm gonna assume this is for some reason, I just don't get why the minus is there, right? But that's the derivative of this whole thing. So this is our basically you know, the density function, probability density. That's probability density. And so what we want to do is we want to do the derivative of this with respect to time, right? Times then whatever like the mass is or something. And that kind of mass thing here is just going to be, I think, that coefficient. Let's just assume it's something like that. The derivative of these is the derivative of these here, right? So the derivative of that is basically how do we do this? So I think we need to expand that. I think we need to just basically say, well, it's 1/2 divided by, and then that's when we kind of have, you know, the function squared plus this times this plus, well, that like 2 times basically, right? And then we have these things squared. And I mean, you can just distribute everywhere, and so we just have that divided by 2, and then plus we just have this thing plus this thing divided by 2, right? Exactly. And so I mean, essentially that is how we get. I just kind of redid the steps of how do we get here, right? Because this term is the one that we get from here. Cool. But and then this is just another way to say, sorry, this is just another way to say, well, that is the how's it called, the inner product. And so because it's the inner product, we can rewrite it like that to see that it's periodic. Periodic. Now, with the derivative of this is the derivative of each of these components, right? And so I think I just calculated that, didn't I? So Isn't the derivative of a square function just 2 times its derivative? Or I mean that's the same as to say that's probably the same as to say, well, like this is the same like this, sorry. And so we apply the same identity that we learned, and so the derivative of that, it's basically saying the derivative of this times this plus you know, this times the derivative of it. All of course divided by 2, right? So that will be one component. Then you have the same here. And then here, I have no idea. I have no idea because I don't know how they get to these fuckers being inside the sinus. It's like, no matter how I think about these, like, it just makes no sense. It makes no sense for the reason that, like, no matter what I end up with, if I will God, if I have these things like that, no, I don't know, man. I just don't see that. Like, I understand that. I can understand. This is intuitive, right? But I just don't get. So, inner product cosine. So you have these, right? Maybe another way to think about this is to say that's how you would express this whole thing, right? You would say that is my but it makes no sense, right? Because the angle between the same function is just 0. that's just stupid to think about it this way. Is 0, so the cosine is 1. So you have these. I don't know. I really don't want to give up. I don't like it. I just want to understand where the fuck does this come from. Man, I guess unless you're saying, well, let's walk it from here again, right? So we have these things, and then if we work the, you know, this is like saying this part here, right? So psi 1x times psi 2x times cosinus of the angle between these, right? And I guess what they're doing here, whatever the fuck WT is here, right? That is just the definition of the angle, because it's like, this is the angle with respect to whatever, I think the horizontal axis or something. This is the second angle. So you minus 1 from the other, and then you also minus WT, whatever the, like, I don't know. What is that? Why? Oh, sorry. I think I made a mistake here. In terms of HW. Yeah, no, I think that is okay. Like, you can make that definition here so that you then end up with the e's canceling. I think that's what's important, because the e's are different here, right? So you end up with just saying like so that those things don't disappear totally. That's my mistake. So these actually don't disappear. It's like you end up with like E1 minus E2. So the energy difference, which here they define as these. So that's something that I don't know. So this is E times h bar, e to the powers of h bar times W. W is the angular momentum, I guess. So this would be, I don't know why you can make that definition, right? H bar times W to the power of E. So you do that. So that stays here, I think. That stays all over the place. Oh. I don't know, but I just have to know. This is one of the things where it's like, it's the damn details, man, that make the difference. But it's really hard for me to understand what is W in here. Is W it's the angular momentum? I don't know. I guess I'll have to work on these. I feel like I almost kind of hand waved all this stuff and it's not that obvious, right? So why can you define the difference of energies being the angular momentum? And how the heck do I get this angular momentum down here and no E at all? Because I get these times its complex conjugate, and so basically the only difference is just the E's are different, right? So you have to define these and then whatever that is. Oh God. Are they just removing the E's out of that picture just because? No, also not. The I stays there. And then what is these? I don't know. This is complicated, and I don't know even how to understand that, how to get that. It's just this is something I don't understand. This is something I also don't understand. Why you can do that? Angular momentum, energy difference. But Google is always our friend. I don't even know how to define angular momentum. It's how fast the ankle moves, I guess. Angular momentum yay. I mean, there's gonna be a direct relationship, right? But I don't know why you just can define that like that. Why can you do that? Why can you just define this? Why can you just set things like that? Oh God, that's gonna be a tough one. But I want to understand all the details. And I just don't know how the fuck to get that sinus in here. but I'm guessing it's just intuitively I just should take that function and do the derivative of it and then multiply by whatever this factor is. That's kind of the mass or something, and that kind of makes sense, right? The flux is the speed at which the rate of change of the probability not mass, that should be an area or something. Why would I say that's mass? The mass density. So the mass per area, I guess. Yeah. So that still makes sense. The mass, and then the density is that's why you put the radius in here, right? Yeah. So that's in a way what defines the mass, but I don't know, that's also something a bit unknown. And then you know, that would be the mass density. It's like the radius times the mass of this thing times, and then the just damn derivative of this thing here. But I just, even if I would take that thing here, I just don't know how to get there. Why would the sinus go outside? I'm pretty confident I'm right with the sort of the intuitive idea, but I just don't know how to mathematically elaborate it so it gets there. Let's look at these, man. Look at these. These, you see these? Is these, right? That's just true. That's Twitter, man. Twitter. You kind of failed me there. I was just maybe too fixed on the fact that this was a definition, and it's just, that's actually the result of simplifying something. You start somewhere, and then that's just the result of how you simplified it. But intuitively, it just makes sense. It's how the probability density changes over time. What I still don't grasp, though, is what does this have to do with the specific, like R, like omega 1 and omega 2? Like, how do I know how to compute these for R, for that specific region? Vanishes at R1. I get it. It's like what it says, like whenever it's R1, it's like one of these functions doesn't exist there, so it's kind of zero, right? And the sign of 0 is 0. Yeah, which makes sense, right? It means it vanishes, like inside, like inside the omega 2 region, it's just that expression. But then as you go out, because both eigenfunctions exist, but then once you're going out of that, this one of the eigenfunctions doesn't exist, namely psi 2, right? Which evaluates to 0, and so the whole expression evaluates to 0, so there's no probability flow, which is weird to think about. It just vanishes. Okay. God. Well, yeah, sure. But still, I don't know how they get that sinus there. I just don't know how to get that sinus there. If that's the thing, and I'm supposed to do the derivative of this, I just don't know how to get the sinus there. How this is even defined. So I have to sleep on it. Anyway, it's been a long one. Cool. See you next time.